Implicit neural image stitching (NIS) is a novel approach that extends arbitrary-scale super-resolution to enhance image quality. This method estimates Fourier coefficients of images to generate quality-enhancing warps, addressing the issue of blurry artifacts and disparities in illumination, depth level, and other factors prevalent in existing frameworks. By blending color mismatches and misalignment in the latent space, NIS decodes features into RGB values of stitched images, resulting in improved image quality. The proposed approach tackles the limitations of previous deep image stitching methods, which often produce low-definition images. By leveraging implicit neural representations, NIS can effectively resolve these issues, as demonstrated through experiments. The authors show that their method outperforms existing techniques, achieving better image quality and reduced artifacts. The key innovation of NIS lies in its ability to estimate Fourier coefficients, enabling the generation of high-quality warps that mitigate color mismatches and misalignment. This is achieved by operating in the latent space, where features are blended and decoded into RGB values, resulting in a more seamless and accurate stitching process. The experiments validate the effectiveness of NIS, showcasing its potential to overcome the limitations of current image stitching methods and produce high-quality, artifact-free images. The proposed method, illustrated in Figure 2, demonstrates two-view image stitching with a single perspective homography. By assuming given aligning transformations, the neural implicit representation, NIR, predicts warped Fourier features with high-frequency details. A CNN-based blender then combines two aligned features into one latent variable to alleviate color mismatch and misalignment. Finally, a decoder generates a representation of the stitched image from the extracted features. The experiments show that the proposed NIR restores local textures while maintaining the estimation of blended features, similar to previous methods. The main contributions of this work are threefold. Firstly, an implicit neural representation for image stitching is proposed, which restores high-frequency details. Secondly, the concept of arbitrary-scale super-resolution is extended to image stitching. Lastly, the model simplifies the image stitching pipeline by performing various tasks, including warping paired images, blending misalignment and parallax errors, and relaxing blurred effects, in a single inference step. The Neural Image Stitching Framework, or NIS, is a novel approach to image stitching that leverages deep learning techniques to produce high-quality, seamless panoramas. The overall flowchart of NIS consists of three primary components: neural warping, blender, and decoder. Neural warping is responsible for estimating the homography between input images, which is achieved through the use of a deep homography estimator, IHN. IHN is formulated for unsupervised training, allowing it to learn from large datasets without human annotation. This enables the estimation of detail-aware features, which are crucial for preserving image details during the stitching process. The blender component is tasked with fusing the warped images into a single, coherent panorama. This is achieved through the use of a learnable blending mask, which is optimized during training to produce visually appealing results. The final component, the decoder, is responsible for generating the output panorama from the blended image features. This is achieved through a series of transposed convolutional layers, which upsample the feature maps to produce a high-resolution output. Through the integration of these components, NIS is able to produce state-of-the-art results in image stitching, outperforming traditional methods in both quality and efficiency. By leveraging the power of deep learning, NIS is able to overcome traditional limitations in image stitching, such as parallax error and ghosting artifacts. The Neural Image Stitching (NIS) model's training strategy is a two-stage process. In the first stage, the model focuses on enhancing high-frequency details through supervised learning with an L1 loss function. This stage is crucial for improving the resolution and clarity of the stitched images. In the second stage, the model concentrates on blending features, constrained by a photometric seam loss to correct color mismatches and parallax errors. This stage ensures that the stitched images have consistent color and minimal distortions, resulting in a more realistic and coherent output. The training process is designed to optimize the neural warping, blender, and decoding INR modules simultaneously, as depicted in Figure 4. This simultaneous optimization allows the model to learn how to effectively combine these components to produce high-quality stitched images. The use of the L1 loss function in the first stage promotes the generation of detailed and sharp images, while the photometric seam loss in the second stage helps maintain color consistency and reduce visual artifacts. By optimizing all three modules together, the NIS model can effectively handle complex scenes and produce seamless image stitching results. Overall, the training strategy for the NIS model is designed to leverage the strengths of each component to achieve high-quality image stitching. By focusing on enhancing high-frequency details and correcting color mismatches and parallax errors, the model can generate visually appealing and coherent stitched images. The evaluation of stitching performance on synthetic images highlights the MPSNR and MSSIM scores for various methods, including bilinear, bicubic, and the proposed neural image stitching, NIS. This is followed by the evaluation on real images, presenting the NIQE and PIQE scores for different methods. A detailed comparison of stitching performance is provided using red and blue colors to indicate the best and second best performances, respectively. The training details focus on the on-the-fly data generation, augmentation strategy, and the blending stage. The training configurations include batch size, number of iterations, and learning rates. The experiment section highlights the datasets used, including MSCOCO and UDISD, and the implementation details such as the deep homographa estimator and neural warping components. Finally, the evaluation results are presented, focusing on the quantitative comparison of stitching performance on synthetic and real images. The proposed NIS method is compared qualitatively with other image stitching approaches on the UDISD real dataset, revealing significant limitations in existing methods such as jagging and blurred artifacts. These issues are effectively addressed by the NIS method, resulting in substantial improvements in image quality. Notably, the NIS method outperforms bicubic and bilinear warps in terms of MPSNR, demonstrating its efficacy in enhancing visual fidelity. Moreover, the fine-tuned NIS model excels in correcting color mismatches and relaxing parallelism, as evidenced by superior performance metrics including NIQE, PIC, and BRISQUE. This underscores the effectiveness of the NIS approach in achieving better image quality through learnable image stitching. Comparisons with other methods, such as LPC plus GraphCut and IHN plus NIS, further emphasize the NIS method's superior performance in enhancing image quality. The results suggest that the NIS approach offers a promising solution for overcoming the challenges inherent in traditional image stitching techniques, ultimately leading to more accurate and visually appealing stitched images. The authors present a qualitative comparison of their method, NIS, with existing approaches on the UDISD real dataset. The results in Figure 5 demonstrate that NIS captures high-frequency details while preserving image blending capabilities. A qualitative comparison of image qualities between UDIS and NIS is provided in Figure 6, supporting the performance gains indicated in Table 1a. The authors also explore the inference of their model under elastic warping, showing that their implicit neural representation for image stitching can recover high-frequency details on unseen aligning grids, as shown in Figure 7. They use robust ELA to estimate the elastic grid and generate the stitched image using NIS. In terms of cost-effectiveness, the authors compare the specifications of stitching methods for 3 different resolutions in Table 2. They report the maximum memory consumption and average computation time, showing that NIS is cost-efficient for lower-resolution images but exhibits weakness on high-resolution images compared to UDIS. An ablation study is conducted to explore the contribution of Fourier features for image stitching on synthetic MSCOCO. The results in Table 3 highlight the importance of frequency priors and the impact of removing amplitude and phase estimators on model performance. The authors investigate the contributions of their training methods in Figure 8, demonstrating that their learning strategy for blended feature reconstruction provides visually pleasing stitched images. Finally, the authors discuss the efficiency of neural warping, comparing their pipeline to LTEW's pipeline for local INR, and highlighting the advantages of their approach in preventing over, undershoot and blocky artifacts for upscale factors greater than 8. The authors conduct an ablation study of their training method, comparing neural warping, northwest, with the state-of-the-art method, LTEW, for high-definition warp. The evaluation configurations remain consistent with previous works, and the results are presented in Table 4. Neural warping exhibits favorable performances in both computational complexity and super-resolution. Furthermore, the authors explore the combination of neural implicit stitching, NIS, with seam cutting, as shown in Figure 9. Seam masks are prepared using OpenCV's DP Seam Finder, and NIS is employed to estimate the stitched image by blending latent variables and decoding the output. The results demonstrate the potential of NIS to be used with seam cutting for advanced blending. The authors propose a novel end-to-end implicit neural reconstructor for image stitching, NIS, which successfully predicts dominant frequencies in warped domains to represent high-frequency details in a stitched image. This approach relaxes parallax errors by blending color mismatches and misalignments. The framework shows significant gains in synthetically stitched datasets over traditional methods, and qualitative results on real images support the achievement of high-frequency details for view-free image stitching. However, the authors acknowledge the limitations of their approach, noting that simplifying the training pipeline for neural image stitching remains an open challenge. Additional strategies for training would be required to design full end-to-end deep image stitching from image alignment to reconstruction. A comparison of neural warping to LTEW in terms of performance on ERPSR and cost efficiency is provided in Table 4, highlighting the advantages of the proposed approach. In the realm of computer vision, image stitching and homography estimation are crucial tasks that enable the creation of panoramic images from multiple overlapping views. Recent research has made significant strides in these areas, with several studies proposing innovative approaches to address the challenges inherent in these tasks. One notable contribution is the SURF, speeded-up robust features, algorithm, which extracts robust and repeatable features from images, facilitating efficient feature matching and homography estimation. This approach has been widely adopted in various applications, including image stitching and 3D reconstruction. Another significant advancement is the iterative deep homography estimation method, which leverages deep neural networks to iteratively refine homography estimates. This approach has demonstrated superior performance in handling complex scenes and varying lighting conditions, making it a robust solution for real-world applications. LaNet, a learning-based approach, has also shown promising results in homography estimation. By leveraging a large dataset of image pairs, LaNet learns to predict accurate homographies, even in the presence of noise and outliers. The key advantage of LaNet lies in its ability to generalize well to unseen scenes, making it a versatile solution for various computer vision tasks. These studies have collectively pushed the boundaries of image stitching and homography estimation, paving the way for more sophisticated applications in computer vision. However, challenges persist, and future work is necessary to address issues such as handling large-scale datasets, dealing with diverse scene geometries, and improving the robustness of these methods in real-world scenarios. This page concludes the research paper by providing a comprehensive list of novel methodologies and algorithms developed throughout the study. The section highlights the significance of these contributions in advancing the field of artificial intelligence, particularly in the realm of machine learning.